Hello everyone, my name is Stephen Gigrich and this is Lab 2, Charge Tape Revisited. As an overview of my lab report, I will first introduce the lab and the physical principles behind it, as well as my lab setup. Then I will go over my lab procedures, observations, and calculations. I will then show you my glow strip simulation and end it off by answering the two questions of the main ideas of the lab. Introduction. Background information and physical principles. Vectors are widely used in physics to convey multidimensional information and consist of the magnitude and direction of a quantity. Coulomb's law states that an electric force is proportional to the charges of two particles and the distance between them squared. This is multiplied by Coulomb's constant, which is approximately 9 times 10 to the 9th, with units newtons meters squared divided by Coulomb squared. The electric field theory states that charged particles emit fields into space that can exert forces, and gravitation is a property of matter to be attracted to other matter. This force is easily described by Newton's second law, F equals ma, where A is replaced by G. Superposition is a property that multiple fields can be added together to form a net field. Derivations of equations and formulas. Uniformly distributed charge is where instead of taking all of the charge q in one equation, we split q into even chunks of delta q. Taking the limit of this, we get dq, an infinitesimally small chunk of dq associated with an infinitesimally small chunk of the tape. Integrating over the length of the tape modeled after a rod, we get these formulas, which are in our class formula sheet. The purpose of revisiting the charge tape experiment was to come at it from a different perspective, one that is more lifelike. Instead of treating the tape objects as single points, we can treat them as multiple points, more closely resembling the real physics with electrons and protons. A secondary purpose of this lab is to help reinforce the concepts of distributed charge and get more practice with the integration methods and ideas. It also increased my proficiency in GlowScript. Here's my lab setup and some gathered data during the experiment. As you can see, for tape A and B, the lengths were 16.9 centimeters and a width of 1.9 centimeters, mass 0.169 grams. The distance between the tapes at the time of flotation was 3 millimeters. Here are the systems and surroundings of my lab. The system is just tape B. The surroundings are everything else, such as tape A, the textbooks, and the earth. The initial conditions were that tape B was being pulled on by gravity, but after tape A was brought near it, it was now also feeling the electric force from tape A. A preview of my experimental results are that U-tapes are positively charged, like charged objects repel while oppositely charged objects attract. The electric field force is significantly stronger than the gravitational field force. A charged tape is able to be floated on top of another charged tape, with the electric force counteracting the gravitational force, and that line charges are a much more accurate model than point charges. Lab procedures and results. The steps I took to conduct my lab were 1. Pull out identical lengths of tape, and measure and record the lengths and widths of the tape. Make a tab in both tapes and place the tapes on top of the table. Rapidly pull both tapes off of the table, charging them. Place one tape across a gap, I use textbooks, and place the other tape below the other one to bring it up until it begins to float, and then measure and record the distance between both tapes. Some observations I had were that like charges repel each other. Both negatively and positively charged objects are attracted to neutral objects, and that the attractive force between the tape and my hand was surprisingly strong, easily beating gravity. Here are some of my calculations. Using the surface density of the tape and the area of the tape, I was able to calculate its mass, 0.169 grams. Using F equals mg, I was able to calculate the magnitude of the gravitational force to be 1.66 times 10 to the negative 3 newtons. Since the floating tape was in equilibrium, the electric force had to equal the gravitational force, and was therefore also 1.66 times 10 to the negative 3 newtons. I did some more calculations to determine the net charge of tape B using net force equations and the modified electric force equation. Setting them equal to each other and solving for Q, I got a total charge of 1.242 times 10 to the negative 9th coulombs. Some possible sources of error in this lab were losing charge from touching the tapes, bad data, the limits of the simulation, namely the N value, which determined how many point charges were in the line charge, the tapes having different charges, and the tapes having different masses. GlowScript program results. Here are two functions that I used. One was to determine the E field from a given particle charge and position. The other was the function creating a line charge object that consisted of smaller point charges. This function determined the individual forces between the particles, as well as the net force between the tapes. This can be seen on the next slide as the green arrows represent the individual forces, while the gray is the electric force on tape B from tape A, and the yellow is the gravitational force on tape B from the Earth. As you can see from my program output, these two forces are equal in magnitude, meaning my net charge calculations were correct. Questions and answers. It was not necessary to ignore air resistance in this lab, as the two tapes are in equilibrium and stationary. Air resistance is a function of velocity, but the tapes were staying still. The second assumption was also not necessary, as was the whole point of the lab, to not treat it as a point charge, but instead as a line charge with a uniformly distributed charge. The third assumption was necessary, as it would be almost impossible to get the two tapes the exact same in terms of length, mass, and charge, so it made the calculations easier and neater. In Lab 1, I got a total tape charge value of 7.434 times 10 to the negative 10 coulombs, while in this lab, Lab 2, I got a total tape charge of 1.242 times 10 to the negative 9 coulombs. This is an increase of around 167%. This answer makes sense as the point charge model overestimates the field strength of the tape. So for the field magnitude to be more accurate, the charge magnitude would need to increase accordingly. In the point charge model, no charge is wasted in the x direction, while with a uniformly distributed charge, charge is wasted as it is cancelled out in the x direction. The line charge method is more likely closer to the real value, because in real life, the tape isn't just 20 charges, 20 is what I use for n, but hundreds of billions of charges, as electrons and protons.